the screen and all that stuff. Okay, so I'm hoping to be on par after today. I'm hoping to finish 2.3. Again, we're skipping 2.4 altogether. We're never going to do it. And then I'll just go to 2.5. Okay. And by the way, 2.4 is not really something you need for any other section. It's completely independent. It's a nice, topic, but you say, well, if I don't cover that, am I going to miss anything from all the others? No, you won't. It's sort of a topic that stands by itself. All right. And a quick reminder of the change here. So 1 to 7 odd, 19 to 27, but only do the odds from 2.2, 2.3, 3 to 31, odd, 41, 45, 47, 53, and we're skipping 2.4 altogether. So because of the weirdness of last week, I should be able to be on par if I follow this schedule now, and we're skipping 2.4, so I can just jump to 2.5. Okay. All right, I'm going to jump over and go back to 2.2 about something. Now, I'm not actually giving you answers for this, but I'll just talk about it. Okay, 2.2, number 37, limit as x approaches pi over 2 from the right of 1 over x secant of x. So if you look back at 2.237, it asks for that. So I'm not going to do it, but I'll just mention some things. Okay, now first of all, I don't know any calculator that has a secant button, right? So if you look at a typical calculator, there's no secant. So, and there's a good reason for that, because you can just use the reciprocals, right? We have sine, cosine, tangent, and we know that secant, cosecant, and cotangent are just the reciprocals. So what is the reciprocal of the secant? It's the cosine, right? So 1 over x cosine x. And that's the reason why you don't have a button in general. Sorry. We don't have a button in general that does secant, cosecant, cotangent, because you can just go 1 over, 1 over, 1 over. Okay. And if you want to put it in your cheat sheet, you may. I wouldn't let you have a cheat sheet if we were meeting, face to face. But just a reminder, one memory trick that I use is if one trig function has a co, the reciprocal does not have a co. So for instance, secant, there's no co, right? So the reciprocal has a cosine. Okay, let's take sine. Sine, there's no co, so the reciprocal has a cosecant. Right, so that's one way that you can remember. So one function has a co, the reciprocal does not have a co. And of course, tangent and cotangent are pretty easy. Most students are okay that tangent and cotangent are reciprocals. All right, so I'm going to write it as 1 over x cosine x. Okay, the other thing you want to keep in mind is that this is in radians. Okay, so if you have your calculator set to, sorry, if I angle this the wrong way, I end up burning your eyeballs out like that. But make sure you're in radian mode. So on my calculator, let's turn it on and check the mode. Okay, I'm in radian mode, but your calculator might be in degree mode, which would be like what? I can aim it right. Okay, so now I'm in degree mode. So switch back and get it to radians. So whatever calculator you have, make sure you're in radians when you do this. And then you approach pi over 2 from the right, and we're not comfortable with doing that. So how do you do that? Because when you approach something like 0, it's easy to approach from the right. That's 0.1, 0.01, 0.001, and so on. How do you do it for pi over 2? All right, so on my calculator, I punch out pi over 2, came out to be about 1.57, and you can do that as well as I can. Many calculators have a pi button, right? So if I hit second function pi and then divide it by 2. So 1.57079, blah, 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 blah. Okay, so if we want to approach from the right, what you do is for each progression, you take the next highest digit. In other words, 1.6. Okay, you know 1.6 is bigger than this, right? Because 6 is bigger than 5. Then the next progression will be 1.58, which is bigger than all this. All I did was take the 7 and add 1. Then the next one is 1.571, I leave the 1, 5, 7, and I just bump that up to a 1. Right? All of these numbers are bigger than this, right? So you want numbers that are bigger than pi over 2. You're getting really, really, really close coming from the right side. Okay, so I take the tenths place, I add 1 to it, so it's 1.6. 1.6 is bigger than this whole number. And then 1.58 is bigger than 1.570, blah, blah, blah. And then 1.571 is bigger than 1.5707, and so on. And then 1.5708 is bigger than 1.57079, and so on. In fact, this is already pretty close. Okay, so in your table, you plug these guys in, and you're only approaching from the right, so you don't have to approach from the left, and don't worry about that. Okay, but I'm not showing you what you get, because otherwise I'm giving you too much. But take all of these numbers, plug it in, and you should see a pattern as to what the values approach. Okay, and likewise for 39, limit as x approaches 2 pi from the left of x cosecant x. Okay, so again, your calculator cannot do cosecant, so cosecant is the reciprocal of the sine. So x over sine x, and 2 pi, that's a minus sign there. I know it kind of looks like it's all 2 pi. All right, so I first get 2 pi. So 2 pi, sorry for burning out your eyeballs. 2 pi, 6.28316, blah, 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 blah. Oh, it's 3.1, whatever. Okay, so now if you want to approach from the left, then 6 is smaller than this, right? Then 6.2, then 6.28, then 6.283, and so on. So those will be numbers approaching 2 pi coming from the left. Punch them in, and then you should see a nice pattern. Okay, and again, you have to be in radians to do that one. All right, so I wanted to emphasize again, that's how you do those problems. Those are a little bit harder. Okay, so I'm not going to give you the answer, but you know what to do. Just plug that in to here, then plug that in to here. When you're typing it in your calculator, you probably should put parentheses here. So put extra parentheses like that. Okay, I don't think you need extra parentheses here. Okay, so that takes care of that. And one more theory about 2.1 that was brought up. So way back in 2.1, remember we had these pictures? So I did this even before the first test. Right? I think this was a Thursday or Wednesday before the exam. I gave you that as a beginning of 2.1. Okay, so the idea here is Q is approaching P coming from the right. Notice P stays the same, right? P is fixed. Here, Q is approaching P coming from the right. So the red is a tangent line. Notice the T, tangent, that stays the same in all of these. But the blue line, the secant line, what's a secant line? It's a line joining 2 points. Okay, it gets closer and closer to the tangent line as Q moves closer to P. And here, Q is moving toward P coming from the left. So the slopes get closer on the left side also. So when you're doing the 2.1 homework, of which there was not too much, okay, you are essentially just finding slopes of tangent lines. So average velocity, okay, so let's say 5A1, lasting 0.5 seconds means you're using 2 and 2.5. Okay, so you plug in 2, figure out the y, plug in 2.5, plug in the y, find the slope. That will be your average velocity because you're going to have feet divided by second. You're doing feet divided by second. And let's say the last one, lasting for 0.01 seconds, means you're plugging in 2. You already did that. 2 is your fixed point. So you plug in 2, and then you plug in 2.01. 2.01 here, 2.01 here. So again, you have 2 ordered pairs. You have 2 comma, whatever you get when you plug in 2. And you have 2.01 comma, whatever you get when you plug in 2.01. Find the slope. Okay. Y is in feet. Time is in seconds, so you're doing feet per second. That's average velocity. Then when it asks for instantaneous velocity is the slope of the tangent line. Okay. And I showed you the picture for number 1 and number 7. I drew a tangent line that was instantaneous velocity. So instantaneous velocity is for the tangent line. Okay. All right. So that's that. Now getting back to more 2.3 stuff, finding more limits. Okay. And 31 actually has two variables, x and h, which wasn't the case for the problems that I did yesterday. So this one's going to be a little bit harder. Okay, so 31, limit h approaches 0, x plus h cubed minus x cubed all over h. Okay. In case you're wondering, you may notice it looks like we're approaching 0 quite a bit. That's true. We're going to be doing derivatives shortly, something called derivatives, D-E-R-I-V-A-T-I-V-E-S. You don't have to write that down. We'll get to that later. But that's going to be the topic for much later, derivatives. In fact, the main concept of all of Calc 1 is derivatives. I mean, you can't really get out of Calc 1 without hearing derivative. After all, we're going to say derivative, 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 derivative over and over and over, so you can't really forget it. Okay, so don't worry about writing it down right now. But yeah, the definition of the derivative involves a limit as h approaches 0. Okay, so you have x plus h cubed minus x cubed all over h. So in this answer, the answer is going to involve x this time. The ones we did yesterday, they all had real numbers as a final answer. Here, your final answer is going to involve an x. All right, so here we go. All right, so 2.331, again, ignore any dates. Limit h approaches 0, x plus h cubed minus x cubed all over h. You cannot plug in 0. Okay, so a very easy question would be simply plugging in directly. Right? I only showed you one problem like that yesterday because that's too easy. I gave you the law that if you can just directly substitute, do it. But that's too easy. That becomes just like algebra 1. So here we have to do some algebra, an algebra trick. So I have to figure out x plus h cubed. All right, so I took a little time out here, figure out x plus h cubed. What is x plus h cubed? The box is my timeout, so to speak. Well, it's x plus h squared times another x plus h. Then I took the time to figure out what is x plus h squared. X plus h squared is x squared plus 2xh plus h squared, right? Using the formula for the square of a binomial. Right? That's like a plus b squared, which was a squared plus 2ab plus b squared. So this is the same as this. And now I multiply by another x plus h. So this thing right here, this is x plus h squared. Now take that times another x plus h, and I get x plus h cubed. Okay. So take x squared times both of these, and then 2xh times both of these, and then h squared times both of these. All right? So here we go. So I'm pointing to the two things I'm multiplying. This is x cubed, right? These two give me x squared h. There it is. Okay, so I'm finished with the x squared. Now it's 2xh times both of these. So these two give me 2x squared h. There it is. That times that is 2xh squared. Okay, so I'm finished with that and with that. Now it's h squared times both of them. So h squared times x, xh squared, and then h squared times h is h cubed. 1, 2, 3, 4, 5, 6 terms. Combine like terms, the things that I have circled here, these are like terms. X squared h plus 2x squared h is 3x squared h. And similarly, 2xh squared plus 1xh squared is 3xh squared. And x cubed doesn't combine with anything. H cubed doesn't combine with anything. So this mess right here is x plus h cubed. X cubed plus 3x squared h plus 3xh squared plus h cubed. Okay, so I'm going to plug all of this mess in right in there. And here we are. So limit h approaches 0 of x plus h cubed, there it is, minus the x cubed all over h. Okay, x cubed cancels x cubed. So I have 1, 2, 3 terms. What do these three have in common? They all have an h. And that's convenient because I'm going to take that h and cancel that h. That's going to be a recurring theme. Notice that theme. That theme is going to show up quite a bit. So I'm going to go h paren, take an h out of that, 3x squared. Take an h out of that, 3xh. Take an h out of that, h squared. Okay. X cubed is gone, divided by h. And very conveniently now I can cancel these h's. That's allowed as long as h is not equal to 0. And you can see here h is not 0. Right? H is very, very, very close to 0 on both sides. Right? There's no plus here, which means only coming from the right. There's no minus, which means only coming from the left. This is two-sided. So this is like 0.1, 0.01, 0.001, 0.0001. That would be coming from the right. And coming from the left would be negative 0.1, negative 0.01, negative 0.001, negative 0.0001, and so on. We're not actually plugging in 0 for these problems. So anyway, these cancel out. Now, by direct substitution, let h be 0, not x, let h be 0. So put a 0 right there. That's an arrow meaning it's nothing. Put a 0 there. That's an arrow meaning that's nothing. So the only thing that's left is 3x squared. So 3x squared plus nothing is just 3x squared. So the final answer is just 3x squared for this one. Okay. Notice my answer actually comes out to be a variable expression, which makes sense because I started off with x and h. Okay. So at a certain point, we're going to be plugging in 0 for h, not here. We have to find a way to get rid of it. Okay. But I won't be able to get rid of x. So notice the problems that I did yesterday, they all came out to be real numbers, but not here. Here, the final answer is 3x squared. Okay. And for some of the problems at the end, 41, find the limit if it exists. 41 is so straightforward, it's just a plug-in, folks. It says limit as x approaches 3 of 2x plus absolute value of x minus 3, just direct substitution. Okay, and I don't think there's going to be any problem with direct substitution. 43, there might be some problem. Yeah, I think there is some problem. So the key for 43 is to do some factoring. I was going to do 45 for you, though. Limit as x approaches 0 from the left of 1 over x minus 1 over absolute value of x. Okay, so let me do that one. All right, x approaches 0 from the left. That's like negative 0.1, negative 0.01, negative 0.0001, and so on. Okay, I have an absolute value expression here. Okay, so I'll take a little time out here and recall, put it over here, absolute value of x is the same as x when x is greater than or equal to 0. We know that, right? Like, what's the absolute value of 7? 7. What's the absolute value of pi? Pi. What's the absolute value of a half? A half. It stays the same if x is greater than or equal to 0, right? But if x is less than 0, right? What's the absolute value of negative 20? Positive 20. So you give me the opposite of the number, negative x, if x is less than 0. Okay, you have to be careful. This does not mean a negative number. This is actually going to be a positive quantity because x is given to be negative. So I say, what's the absolute value of negative 1? That falls under this category. So you give me the opposite of negative 1. In other words, the negative of negative 1, which is a positive 1. So this is correct. Okay, now, based on this, x approaches 0 from the left means I'm only plugging in negative numbers. If I'm only plugging in negative numbers, I'm doing the bottom part. I'm completely ignoring the top part. Absolute value of x is negative x. Okay. So I change the denominator to negative x. I'm only plugging in negative numbers. Since I'm only plugging in negative numbers, I'm doing the bottom part. So temporarily, it's negative x. So it's minus a minus x. That little symbol there means I'm making them a positive because it's a double negative. So that's supposed to be a negative. That's supposed to be a negative, but that becomes a double negative. So I'm making it to a positive. So it's 1 over x plus 1 over x, which is 2 over x. Okay, so now limit as x approaches 0 from the left. Now, you could do this by plugging in, but I think you should get some familiarity with the concept that if I divide by a very small number, what happens when you divide by a very small number? You get a very large number. Okay? So yes, you could chart out negative 0.1, negative 0.01, negative 0.001, negative 0.00001. You don't have to though. If I say 2 divided by a very small negative, if I divide by a very small negative with 2 on top, I get a very large negative. So the answer is automatically negative infinity. Okay, so that's what I want you to take away from that one. So that's the answer to 45, negative infinity. Okay. All right, ignore all these notes here. I'm not even going to show it to you. So we're skipping 2.4 in case you want to see a little bit of what you're missing. This is what you're missing. Anyway, 53, we're going to pull over and park there for a while, so to speak. It's the greatest integer function. It's going to take a while to develop this. Okay, so we call it the greatest integer function. It's kind of funny. It's like double brackets, greatest integer function. Let me give you some questions about it. So I just talked about it very quickly last time, but let me go over more on the greatest integer function. Okay, top of 101. And unfortunately, I have to keep switching back and forth in the book. But greatest integer function, I've seen it several ways. Sometimes they just put a bracket or double brackets. But it's the largest integer that is less than or equal to x. Okay. Now, if you already have an integer, the greatest integer function will leave it alone. What are integers? Integers are 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. There's no fraction part. There's no decimal part. Okay. If you already have an integer, you leave it alone. So greatest integer function of 3 is 3. Greatest integer function of negative 4 is negative 4, if it's already an integer. But if you have any fraction or decimal part, you always round down. You will round down any fraction or decimal part to the nearest integer. Okay? So they give you some examples here. Greatest integer function of an integer, 4, stays 4. Greatest integer function of 4.8 is 4. You always round down. You do not round off. If I said round off, you would say 5. Greatest integer function always goes down. So if you have any fraction or decimal, like the 0.8, you will go down to 4. Greatest integer function of pi, pi is 3.1415, blah, 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 blah. Greatest integer function would be 3. Okay. Greatest integer function on square root of 2. Square root of 2 is like 1.414, blah, 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 blah. So rounding down would be 1. Greatest integer function of negative a half, okay, if you go down, that would be a negative 1. Okay. And I have some other examples here. So even greatest integer function of 4.99, it's not going to be 5. You have to go down to 4. Okay. Greatest integer function of pi, we said was 3. But here's a trap you have to watch out. Greatest integer function of negative pi is not negative 3. It's negative 4. Because negative 3 would actually be increasing. You have to go down. So going down from negative 3.14159, blah, blah, would be a negative 4. It's a little bit tricky. The function is sometimes called a step function. This is what it looks like because it looks like you're climbing steps. Okay, closed on the left end, open on the right. So close, open, close, open, close, open, close, open. Okay. Let's take an example, stuff between 0 and 1. So greatest integer function of 0 stays 0. 0.1, 0, 0.2, 0.3, 0.4, 0.5, 0.9, 0.9, 9.999999, you're still going to go down to 0. But once you hit 1, greatest integer function of 1 jumps up to 1. And then 1.1, 1.2, 3, 4, 5, 6, 7, 8, 1.9, 1.99999. greatest integer function would still be 1. And then once you reach the 2, it jumps up again, right? So it looks something like this. And side note, if you ask for the domain is all real numbers. Can you guess what the range would be? What's the set of all y values? The set of all y values is a set of integers. You can only come back with an integer. Okay, so that's 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. So the range would be the set of integers. Okay, now, in order for me to get the questions, I have to bounce back and forth, sorry. So this picture of the greatest integer function is on 101, but the questions for 53 is on page 104. Okay, so unfortunately I have to go back and forth, and I know the print is not very big. So it's going to be a little bit awkward here. But A says, limit as x approaches -2 from the right. The plus means coming from the right. Okay, limit as x approaches -2 coming from the right. Okay, x approaches -2. Here's -1, -2. X approaches -2 coming from the right side. Well, we approach the y value of -2. In fact, it is -2. Okay, so the answer to the first one is -2. If we approach -2 coming from the right, we get -2. Part B, limit as x approaches -2. There's no symbol, so it's double-sided. So we approach -2 from both the left and the right. Okay, so I guess this is, the first one was AI. This one is now AII, I guess. So approaching -2 from both sides, well, we already know that if we approach from the right side, we're at -2. They don't show up, but there's another piece that's down here, right? It's a step function. So coming to -2 from the left, there's a piece down here. So where's down here? That looks like it would be -3. Right? So the two-sided limit does not exist. Coming from the right, the limit is -2. Coming from the left, however, the limit would be -3. Right? So the two-sided limit does not exist. So the answer to 53AII would be DNE, but does not exist. DNE. By the way, the back of the book also puts DNE, does not exist. DNE. Part 3, two-sided limit as x approaches -2.4. We approach -2.4. Well, you know -2.4 is going to be down here somewhere, right? So it doesn't matter if I'm a little bit to the left or a little bit to the right. We round down to -3. Right? So the answer is -3. Right? So part AII, the third part, is -3. And that's also borne out by the fact from the graph, but also if you think about it, x approaches -2.4 both from the left or from the right. Well, if I have the greatest integer function of -2.40001, or -2.3999, either from the left or from the right. In either case, I'm going to go down to -3. Right, so that doesn't change. Okay, so the answer to part 3 is -3. All right, now, if n is an integer, evaluate the following. X approaches n from the left, x approaches n from the right, where n is an integer. Okay, so maybe the best way to do that is to think of an integer. All right, so let me just pick a number like 1. See what happens with 1. Trying to get a piece of paper here. So what is the limit as x approaches 1 from the left? And the limit as x approaches 1 from the right of the greatest integer function. Okay? So x approaches 1 from the right side. So when x gets really close to 1 on the right side, the y values are up at 1. 1. How about as x approaches 1 coming from the left side? I'm down here. 0. And you stop and think about it, it makes sense. What's the greatest integer function of, okay, so I'm going to approach 1 from the right. 1.1, 1.01, 1.001, 1.001, 1.001. All of those, if you apply the greatest integer function, would give me 1. Now, approach 1 from the left. 0.9, 0.99, 0.999, 0.99999, 0.9999999. All of those, if I apply the greatest integer function, would go down to 0. So it looks like we reduced by 1. All right, so now that we have that, let's apply that to the question. If n is an integer, what's the limit as n approaches, as x approaches n from the left and x approaches n from the right? So we're doing 53b, I, and I guess. So got to get back that graph. So here was the graph. So limit x approaches n from the left, limit x approaches n from the right. Okay. So look what happened over here. That 1 matches that 1. So if we approach on the right, that number stays the same. So it looks like over here, n. Approaching from the left, what happened here? 1 went down to 0. So it reduced by 1. All right, so reduced by 1. N minus 1. So here are my answers. And yeah, you want the exact numbering? Sorry. Get that here. That would be what? 53BI. So this is 53BI. And this is 53BII. All right, and finally, part C. For what values of A does the limit as x approaches A of the greatest integer function exist? So 53C, if you can't read it. Exists for which A. Limit as x approaches A, two-sided limit. Does this exist? Well, it worked for negative 2.4, didn't it? Negative 2.4, we got it? Okay. Again, look back. Because we have a jump, 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 and so on, we're not going to have a two-sided limit here or here or here or here or here, wherever we have a jump. So where are the jumps? The jumps are the integers. Right? It jumps up at 0 and 1 at 2. I mean, ask yourself, for what x values do you step up on this? You know, if you can imagine that you're actually climbing the steps, where do you jump up? At negative 1, 0, 1, 2, 3, 4. You don't jump up at the non-integers, like negative 2.4, and so on. Right? Right. So the answer for this is the two-sided limit. Two-sided limit exists for all non-integers. Non-integers. because for the integers, the limit from the left and the limit from the right weren't going to be the same, right? In fact, it's exactly the picture that I have here. You can see over here. If I come from the left, it's lower than coming from the right. But if I pick any in-between point, like 0.5, okay, 0.5, well, it doesn't matter if I'm coming from 0.949 or 0.51, all those values would jump down to 0 when I apply the greatest integer function. Right, so the answer to C is the two-sided limit exists for which values of A? All the non-integers. All right, so that's what we have for that one. Okay, so now I'm done with 2.3. Again, we're skipping 2.4 completely. It's on something called the precise definition of the limit. We're not worried about that. And I'm ready to start some of section 5. So if we throw out 2.4, which we are, maybe I should say since we're throwing out 2.4, we're okay time-wise. And what time is it now? It's about 10 minutes to. So last few moments or minutes, I will give an introduction to what's going on in 2.5. Okay, so you can skip 2.4 altogether. We're not doing any of this. But what is 2.5 about? Introduction. I can turn the pages here. The concept is continuity. Page 114. So we will say a continuous function. Continuous function. We can have a continuous function. And what would be the opposite of continuous? Well, we can say discontinuous or not continuous. So you might hear me say discontinuous, D-I-S. D-I-S meaning no, not, or just not continuous. Okay. Crudely speaking, for a continuous function, okay, you don't have to write this down, but for a continuous function, most of the functions that we know of are smooth, continuous. It means you can graph it without lifting up your pencil from the paper, right? So for this graph, I can graph the whole thing. I never have to lift up my pencil from the paper, right? This one, the function is not continuous or discontinuous at several points, okay, because we come here, there's an open circle here. That means I got to pick up my pen and keep going. So now it's continuous again, continuous. Whoop, discontinuous or not continuous at 3, because I have to jump up over here. Now it's continuous again, continuous, continuous. Then it looks like at 5, I have to jump up again to put a dot there. So discontinuous or not continuous, and continuous again. So very crudely speaking, a continuous function is a function where you can graph it without lifting up your pencil from the paper. Okay. Now, most functions that we're familiar with are continuous, at least wherever they're defined. So let me just draw some functions right here. Okay. So if I have y equals x squared, I'm not even going to draw the axes. That looks like it's continuous everywhere, right? I have the sine function. It's continuous everywhere, right? If I have a straight line, it's continuous everywhere. Okay? So these are continuous everywhere. Okay? And after a while, it gets too tedious to keep writing continuous. I will abbreviate cont, C-O-N-T, and you may do likewise if we know we're talking about continuous, and you get too tired of writing C-O-N-T-I-N-U-O-U-S. I might just write cont for continuous, and discont, D-I-S, for discontinuous. Okay? So y equals x squared, continuous everywhere. Sine function, lines, continuous everywhere. Okay? So what's an example of a function which is not continuous everywhere? Well, how about y equals 1 over x? Do you recall the graph of y equals 1 over x? What does that look like? Okay, looks sort of like this. And you might remember, if you ever forget, you can plug in numbers. Like, what do you get when you plug in 1? 1, right? Then if I plug in a super big number, like 1,000,000, you have 1 over 1,000,000, that's like nothing. And I cannot plug in 0, but I can plug in a number close to 0. If I plug in 0.0000001, this gets real big, so it looks like that. And yes, we know that this is an odd function. It has symmetry with respect to the origin, so I have a branch over here. Or again, you can do plugging in the numbers game. Like, what do you get when you plug in -1? -1. If I plug in a super big negative, -1 billion, this is almost 0, but it's below. It's a very small negative, so it goes like that. And if you plug in like -0.0000001, you get a super big negative number, so it shoots down like that. All right, so there is one x value where the function is not continuous, right? So notice continuous, continuous. I can graph it without lifting up my pencil and paper. And then, oh, I got to jump up where? At x equals 0. And you can tell you're not even allowed to plug in 0, right? So at x equals 0, pick up the pen, and then the rest of the time it's continuous again, right? I can draw the rest of the graph smoothly without picking up my pencil from the paper. So here's a function which is not continuous, not continuous at x equals 0, but continuous everywhere else. Okay. So we would say we have a discontinuity, fancy word, discontinuity. So we can talk about continuity, discontinuity at a certain point. All right, so I'll show you this picture right over here. At x equals a, right here, we would say the function is continuous, right? This whole graph seems to be continuous. I draw it fairly smoothly. Right here, it's continuous. I don't have to pick up my pencil from the paper and so on, right? Function is continuous everywhere. And once again, over here, it looks like the function is not continuous at x equals 1, x equals 3, and x equals 5. It is continuous here. Then, whoop, got to pick up your pen to keep going. So discontinuous at x equals 1, then continuous, continuous, continuous. Oh, at x equals 3, I got to jump up again. So discontinuous at x equals 3, then continuous, continuous. Oh, right at 5, I got to jump up and draw that dot. So discontinuous, and then keep going after that, continuous after that. All right? So very crudely speaking, the idea of a continuous or discontinuous function. All right, so the greatest integer function that we saw earlier, okay, right now on page 116, step function. Okay, so where is the function discontinuous? At all the integers, at -1, 0, 1, 2, 3, discontinuous. But it is continuous in between, right? Like at 2.4 and 2.7, it's smooth, it's continuous. Okay, it's only discontinuous at the integers. All right, now, lifting up your pencil from the paper, that's not a very formal definition of a continuous function. Okay, so I'm going to show you, and I probably won't have time for anything else, but here's the very formal definition of continuity. Okay, it's on the bottom of page 114. So you can write it or not, it's in your book, but here it is. It may not make sense right now, but a function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. And yeah, right now you don't know what this is talking about. I'll explain it more tomorrow, I suppose. Okay, but here's a formal definition. Is a function continuous at a point or not continuous at a point? Okay, the point we're talking about is a. The function is continuous if the limit as x approaches a of f of x equals f of a. Now, that implies certain things. The function has to exist. So the function doesn't even exist at x equals a. It's automatically not continuous. Like this one. You know the function is not defined at 0, so automatically the function is not continuous at x equals 0. You have to jump at 0 because there's no dot at x equals 0. 1 over 0 is a no-no. Right? Okay, then the other thing I notice is that the limit, two-sided limit, has to exist. So if the limit does not exist, that's automatically a condition where the function is not continuous. Okay. And then, of course, it looks like the limit and the function have to match. Okay. So I'll just show you this very quickly, and then I'll stop. Okay. So this is the top of 115. F of a has to be defined. Okay. So continuous at x equals a. Why is it continuous right here? Okay, the function has to be defined. So if there's a hole there, right? If there's a hole, automatically it's not continuous. The limit has to exist. The two-sided limit has to exist. Okay, so if I approach A coming from the left and also coming from the right, the two-sided limit exists. And the limit and the function are the same. We saw examples where the limit exists and all of a sudden they have a dot way down here. Okay? Or it jumps up. Here's a good example. The two-sided limit exists, it's down here, but there's a dot up here. So here the limit would not match the function. So we have to have all of these existing or being true. In essence, you only have to really worry about number 3. Limit as x approaches a, f of x equals f of a. This implies the limit exists, it implies the function exists, and that they're equal to each other. All right, so that's an introduction to continuity. So we're just about out of time, so we'll continue with this tomorrow. So stop to share. Anything quickly in the chat? Let's see. Yeah, sorry, I don't have time for questions for somebody who asked. Come during office hours or ask me tomorrow. Michael, send me an email. And anybody else who missed the roll call, send me an email for that. Okay, so I think that's about it for today, folks. All right, so have a good afternoon, and we'll see you tomorrow. Okay, bye, everyone.
Thank you.
See you.
Yeah.